네, 안녕하세요. 오늘 제6회 대구국제컴퓨터음악제에 오신 여러분 환영합니다. 오늘 6번째 DICMF를 맞아 영국 버밍엄 대학교에서 스콧 윌슨 교수님을 모시고 암흑물질, 새로운 물리학의 소리와 창조적인 만남이라는 제목으로 특별 세미나를 준비했습니다. 저는 오늘 통역을 맡은 김가빈입니다. 이번 음악제에서 특별 세미나를 강연해 주실 스콧 윌슨 교수님에 대해서 제가 간략하게 소개해 드리도록 하겠습니다. 프로그램에서와 같이 스콧 교수님은 영국 버밍엄 대학교에서 작곡과 전자음악을 가르치고 계시고 버밍엄 일렉트로 어쿠스틱 사운드 시어터의 감독이십니다. 그럼 스콧 윌슨 교수님을 박수로 맞이해 주시기 바랍니다. Good afternoon, Professor Scott. Would you like to say hello to the audience and introduce yourself, please?
Hello, audience. It's nice to see you here today, and thank you, Gabin, for being here. I thank you, Gregory, and the festival for the invitation. I'm just going to talk a little bit about a project which has several different aspects to it. And I will pause every once in a while, and Gabin will try to translate into Korean, and hopefully we can all understand and have a conversation together. And if anyone has a question, we'll have questions at the end, but we can also stop in the middle and have questions. That's also fine.
네, 대구에 이렇게 오게 돼서 정말 기쁘고 이제 프로젝트에 관해서 말씀드리려고 하는데 각각의 다른 특징을 가진 이런 프로젝트 안에서 여러 가지 음악적인 것들을 보여드리려고 합니다. 그래서 세미나가 끝나고 한번 질문도 받아보면 좋을 것 같고 좀 자유로운 분위기 속에서 대화가 진행되길 희망합니다.
Was that a good sort of pace? Yeah, okay. So the project is called Dark Matter, and it's a project that we started with CERN in Switzerland, which is the European Atomic Research Center. And they're basically, you may know, they're looking for things there like what they call new physics. So they're trying to find new particles, new aspects of reality. So for instance, they found the Higgs boson some years ago. You may have heard about this. And one of the things that they're trying to figure out is what's called dark matter, and the observable universe. When they look out, they can see, because they can detect gravity, that there must be a certain amount of mass, but they don't know what most of it is, actually. So that's what they call dark matter. They can detect it, but they don't know what it is. So they're trying to figure that out.
이 프로젝트는 CERN이라는 유럽 원자핵 공동 연구소에서 진행된 프로그램인데요. 일단 이 연구소는 스위스와 스위스의 이제 국경에 있는 그런 연구소인데요. 여기서 이제 입자 물리학을 주로 연구를 하는 연구소입니다. 그래서 새로운 입자들을 발견하려고 계속 연구를 하고 있고, 이제 최근 몇 년 전에는 힉스 보슨이라는 입자를 발견하기도 했습니다. 그래서 이제 암흑 물질이라는 것은 저희가 이제 눈에 보이는 뭐 별과 뭐 은하 같은 것을 그냥 물질이라고 표현을 하고요. 그다음에 암흑 물질은 그 감지는 되지만 저희 눈에는 보이지 않는 것이라고 합니다.
Okay. So the project has a number of aspects. It started out as a project for our laptop ensemble. When one of the people who plays with us, my friend Konstantinos Vasilakos, came to us with a proposal to work on this, and then it kind of came into an educational aspect, working with people at CERN. They do a lot of education and outreach, and then finally there's a kind of orchestra piece with electronics and video, which came at the end of that. So it was several years of work.
이 프로젝트는 랩탑 앙상블로 시작해서 그 콘스탄티노스 바실라코스라는 작곡가와 함께 시작된 프로젝트고요. 랩탑 앙상블에서 이제 교육적인 측면으로도 넘어가고 이제 마지막에는 오케스트라 곡을 연주하게 되는 것으로 마무리가 됩니다.
Okay. So the laptop ensemble is one that we have at the university in Birmingham. It's called the Birmingham Ensemble for Electroacoustic Research, which if you're paying attention, you will see spells beer. It was a little bit of a joke because at the university they really like acronyms, so we thought we'll make a funny one. But it was started in 2011, and it uses what's called live coding. And live coding is creating music using algorithms or programs that can be rewritten while they're running in some way. And I'll maybe do a little demonstration of that in a minute. But also uses networked music systems. So that was a big interest of the group, that we were connecting the computers together via a local network and using that as a kind of way of structuring what we were doing, or having ways of intervening in what we were doing in what was usually improvisation.
이제 랩탑 앙상블에 대해서 설명을 드리려고 하는데 여기 버밍엄 앙상블 for Electroacoustic Research라는 앞글자를 따서 주로 비어라고 부르고 이런 좀 재미있는 이름을 붙여서 아주 좋다고 합니다. 그리고 이제 이 앙상블은 2011년부터 시작되었고, 그다음에 라이브 코딩을 사용을 해서 연주를 합니다. 그래서 좀 이따가 예를 보여드리도록 한다고 하고요. 그다음에 이제 이 라이브 코딩은 그 알고리즘을 사용해서 음악을 만드는 것이고, 그다음에 이제 즉흥 연주가 가능한데 이 라이브 코딩을 실행시키는 동안에 계속 즉흥적으로 다시 변형시키고 다시 쓸 수도 있고 이렇다고 합니다. 그리고 두 번째로는 이런 랩탑들을 로컬 네트워크로 연결을 시켜서 좀 구조화를 시키고, 그다음에 이제 서로 연결시켜서 뭐 정보도 주고받고 할 수가 있다고 합니다.
So the project, as I said, was that we started with them was a collaboration between the ensemble and CERN, and specifically with what's called art at CMS at CERN. CMS is one of the two major experiments on what's called the Large Hadron Collider, which is the world's biggest particle accelerator. If you care, it stands for Compact Muon Solenoid. I don't know if you can translate that easily, but basically what we were doing was we were taking data that they were getting from colliding protons together, and we would do what's called sonification of that data. So we would take that data. It was actually from something called the scouting stream. They have a problem there that they're producing huge amounts of data all the time. So they have to kind of decide what to keep. And the scouting stream was kind of the first pass at deciding what might be interesting, that might show new physics. And so we would take that data and use it, basically convert it into and scale it to use it as parameters for synthesis algorithms to make sound.
이 프로젝트는 그 원자핵 공동연구소에서 Art at CMS라는 이름으로 진행된 예술 프로젝트인데요. 그 연구소에는 라지 헤이드론 컬라이더라는 세계에서 가장 큰 입자 가속기가 있다고 합니다. 거기서 많은 실험들이 진행되는데, 거기서 이제 양성자들이 충돌해서 얻은 데이터를 가지고 소니피케이션이라고 해서 음향화를 시키는 작업을 했습니다. 그래서 저희가 사용한 그 데이터의 이름은 스카우팅 스트림이고, 여기서 아주 방대한 양의 데이터가 나옵니다. 그래서 그것들을 이제 파라미터라이즈해서 음악을 만든다고 합니다.
So this was a kind of multi-stage project, and we had performances all over the world, really. In Britain, in Canada, in Turkey, in Athens, at CERN. We played once in a taverna in the mountains of Greece, which for actually some olive farmers, which was quite interesting. And we did workshops, and as I mentioned, various kind of spin-offs, including the orchestra project.
저희는 이 프로젝트를 가지고 여러 나라에서 연주를 했는데, 영국, 캐나다, 그다음에 그 CERN이라는 연구소에서, 그다음에 그리스의 타베르나, 그리스에서, 그리고 터키의 타베르나 라는 곳에서 올리브 농부들과 연주를 하기도 했다고 합니다. 그래서 이제 여기서 파생된 다양한 프로젝트들이 또 있었고 끝내는 이제 오케스트라 곡까지 만들게 되었습니다.
Now I have to pop out of this for a minute. So I'll play you now just a little bit of, we have a kind of trailer here about the laptop ensemble part of this. So I'll just play you a little bit of that and talk a little bit over that.
그러면 이제 랩탑 앙상블을 조금 짧은 트레일러를 한번 보실 수 있고요. 거기에 대해서 더 얘기해 보도록 하겠습니다.
So. You can see I was much younger then. Sorry, dumb joke. So you can see there's also different visualizations of the data while it's being sonified. Some of these are more abstract than others. This particular one is very abstract, was created by Winston Jung, who was a member of the ensemble.
여기 보시는 비디오는 그 물리학의 데이터를 받아서 시각화를 시킨 그런 비디오고요. 그다음에 이 음악은 저 비주얼라이제이션은 아주 추상적인 게 그렇게 만들어졌다고 합니다. 그래서 윈스턴 융이라는 분과 같이 작업을 했다고 합니다.
I'll just move forward a little bit here, and you can hear some different sounds. Maybe a bit different if I look. Sorry. Oh, the internet is being unhelpful. Well, hopefully it will come in a moment. Try again. Well, that was a good theory. It doesn't have to sound like that. It can sound like different things. But I will try just a minute. I'll see.
항상 이렇게 뭐 소리가 날 필요는 없고 다른 방향으로도 얼마든지 만들 수 있다고 합니다.
Oops. It was going for a minute. It's very unhappy. Sorry about this.
양해 바랍니다.
Well, it's a bit hard to see, but uh-oh. Okay, I'll try the other one. So this visualization in this one is a little bit more like a more direct representation of what you might have seen at the point of collision, where you have particles which have shot out in different directions. But hopefully that will play in a moment, but we'll see.
요 장면은 그 입자가 충돌을 할 때 뭐 이렇게 이제 충돌을 해서 폭발하는 입자가 튕겨나가는 그런 모양을 조금 직접적으로 표현했습니다.
Okay.
I think this one.
Oh, that one's better. Okay. Sorry, this was working before, but it's currently unhappy. I'll give it one more try, and then I'll move on if it doesn't work. But oops, that looks better. See if I can. Oops, come on. Try again. Come on. It's connected now, but it's not working.
새로워진 다운이
Sorry. A word from our sponsors. Okay. Now I can try again here. Okay, that's a bit better. So you can see these representations are maybe a little bit more like what you would expect in terms of particles shooting off from a center, or like a snapshot in space of them.
이 장면은 그 입자들이 중앙 지점으로부터 폭발해 나가는 장면이라고 합니다.
Okay. Go back to the slides now. Okay, so I'll say a little bit about sonification for anyone who's not familiar with it.
이제부터 소니피케이션이라는 것에 조금 낯서신 분들을 위해서 한번 설명해 보도록 하겠습니다.
So basically, this is basically refers generally to rendering sound in response to data and interactions. Sometimes people call it auditory display, and it's in this sense it's analogous to visualization. So when you think of like a graph or a chart which visualizes some data, this would be like the sonic equivalent of it. And just like with a visualization, you can have good visualizations which tell you important things about the data, and you can have bad ones which hide important things about the data. Sonifications are like this too. And there's a certain, there's a big aspect of interpretation to this. You know, people sometimes say a sonification is the sound of something, but particle collisions don't sound like anything. So we're making choices in terms of what they will sound like.
소니피케이션은 데이터에 반응을 해서 소리를 음향화시키는 것입니다. 그래서 저희는 이것을 오디토리 디스플레이, 청각적 표시 장치라고도 하고요. 시각화를 시키는 것과 비슷합니다. 그래서 예를 들자면 좋은 시각화는 중요한 사실을 잘 보여준다는 것이고, 나쁜 시각화는 그 중요한 사실을 숨기고 있는 것일 수가 있겠습니다. 그래서 여기서는 사람들이 조금 오해를 하길, 여기 물리학의 소리라고 하면 암흑 물질의 소리라고 하면 그 소리인가라고 오해할 수도 있는데 이것은 그것이 아니라, 왜냐하면 저희가 직접적으로 암흑 물질의 소리를 들을 수가 없기 때문에, 그래서 해석적인 부분이 들어갑니다.
Okay. So one of the problems you have with sonification is, of course, you get some data which has some different parameters, and it will have particular ranges which are appropriate to what it's measuring, but those may not be the same ranges as you want for your synthesis parameters. So we have to do a process of mapping. So we might scale the range of the data to something that's a little bit more sensible. Basically, we have these parameters like phi and eta. Actually, what you get is for each subatomic particle, you have a position basically for it, and they're basically 3D coordinates, but they're specified in this funny set of values called pseudo rapidity for some reason. And so we might say take, as we see here, like phi and map it to loudness and eta to duration, or something like this. So we can make these kind of decisions and do it with live coding. We can make them as we play.
여기 이제 그 데이터를 소니피케이션 하는 방법으로 이제 파라미터를 베이스로 한 이런 매핑 방법을 사용하고 있는데, 이 매핑은 하나의 값을 다른 값으로 대응시키는 것을 말합니다. 그래서 이제 여기 보시면 파이는 피치, 파이라는 그런 데이터는 피치 음정으로 표현을 하고, 그다음에 에이타 같은 경우는 뭐 볼륨이라던가 뭐 길이라던가 그런 것으로 하나씩 지정을 해서 음악을 만든다고 합니다.
This is a video of a visualization of the collision. And this is maybe like a kind of visualization of the data that would come to us for an individual collision. So it's like almost like a photograph instant after the collision, and you can see all these different particles of different types that have shot out in different directions. Maybe I'll just play that again while you're translating.
방금 보신 거는 그 충돌하는 입자들을 사진 찍은 것처럼 그 충돌 직후에 사진을 찍은 것처럼 3D로 표현을 한 것이고요. 그래서 각각의 다른 입자들이 다른 방향으로 퍼져 나가는 걸 보실 수 있습니다.
As I mentioned, it's a massive amount of data produced, something like 1 billion collisions per second. And then that stream of data is they select initially 100,000, and then further tests they give about 100 most interesting collisions per second, and that would be like what comes to us.
이 충돌은 거의 1초에 10억 번의 충돌을 한다고 합니다. 그래서 아주 방대한 양의 데이터이기 때문에 그것을 이제 수를 조금 줄여서 중요한 것을 조금 선별해서 그 데이터가 여기로 온다고 합니다.
Okay, so I'll maybe do a little demonstration of what looks like for the performer, just so you can see. So I have to step over here. So we work with the ensemble in Super Collider, and you can see there's a kind of interface here, and I have a list of, these are all just different collisions, basically, and I can select different ones, and you can see they look a little different, and I can kind of turn them around or zoom in and out, this sort of thing. And I also get some information here about the ranges of values in each collision.
저희 랩탑 앙상블에서는 슈퍼 콜라이더라는 인터페이스를 사용을 해서 이것을 음량화를 시키고요. 그래서 아까 이렇게 하나씩 클릭하는 것이 하나의 충돌입니다. 그래서 이것들을 선택을 해서 돌려보거나 확대시킬 수도 있고, 그 다음에 범위를 지정할 수 있게끔 정보들을 확인할 수 있습니다.
And we have this kind of idea in the way that we've done this, that you have an active collision that you've selected that's being sonified, but then you can change that while it's playing so that you hear the same sonification strategy with different collisions.
그래서 이 많은 충돌 중에서 몇 가지를 지정하는데 그 지정하는 충돌을 액티브 컬리전이라고 말합니다. 그래서 이제 같은 방법에다가 여러 가지 다른 충돌들을 집어넣으면 다 다른 소리가 난다고 합니다.
Okay, so if I just go here, I can maybe just give you a short example of this. So I'll start this playing. So if I switch the collision, and I can do things like change the algorithm, make it slower. I could add another octave. Or some other interval. Sorry, a little hard to do this one-handed, but make it less resonant. And so on and so forth, or change the range of frequency. Okay, so just a very simple example.
이런
Yeah.
간단한 예를 보여드렸는데, 그래서 아까 이렇게 여러 가지 그 충돌하는 이벤트들을 클릭을 하면 계속 음악이 바뀌고요. 뭐 알고리즘을 느리게 설정하면 뭐 음악이 느려지고, 그 다음에 옥타브를 추가하거나 아니면 뭐 성부를 추가하거나 그 다음에 더 울리게 설정하는 등 정말 다양한 방법이 있습니다.
And maybe just to say a little bit more about the live coding, so maybe what's different from this than say like building a software instrument into something like Max or something else is that I can kind of rewrite the whole software instrument while I'm doing this, and sort of, I mean, I've obviously prepared something here, but I could just write one of these from scratch if I wanted to, which is very powerful in some ways, but also has some limitations. So I sometimes say like you can do almost anything you want, but not necessarily very quickly.
라이브 코딩에서 대해서 조금 더 말해보자면 흔히 많이 쓰는 맥스와는 조금 다른 인터페이스인데요. 여기 특징이 원하는 것은 뭐든지 할 수 있지만 조금 느릴 수 있다. 이것이 포인트고요. 정말 한계가 없다는 점에서 그것은 장점이지만 또 어떤 면에서는 또 조금 원하는 것을 다양하게 한다는 것은 장점이지만 어떤 부분에서는 조금 한계가 있을 수도 있다고 합니다.
It's maybe a good moment just to ask if anyone has a question, or should we keep going? Oh yeah. Yeah, so I didn't want to get too into like explaining everything in the code because I think people would get. I mean, it's okay, but I didn't do it because sometimes it's a bit much. But this particular sound is a kind of resonator that's been hit with a noise burst, and so basically, you can see here it says MIDI note. So this is just taking one of the constituents. This one called eta. One of the parameters from the collision, and it's mapping it. So it comes into here in a range between 0 and 1, and then I'm mapping it to be between 50 and 200, and then converting that to MIDI notes and rounding it so I get MIDI pitches, but I wouldn't have to do that. It could be something else, for example. Then I'm using another component for the decay of the resonator. But that's just one example. So I mean, just for fun, if I come over here, I have some other ones. So I can do something like this should actually be something like this now. So I could. This is just sine waves. Doing these kind of sweeps between values, so it's sort of sweeping between the values of different particles, and this one is just some kind of noisy stuff. And then I could also, for instance, plug that into something like a compressor here. You could do further processing to it, this kind of stuff. But that's all from the same data. So I mean, it shows like it doesn't have to sound like something. I mean, I always laugh a little bit like when you hear somebody, like it shows up in the news, somebody like the sound of climate change or something, and you hear this really sad kind of music. And it's sad because it's not because, climate change is sad, but the music is sad because the person decided to map it onto something that would sound sad. So you're making choices. But I think from our perspective, what's also interesting about working this way is that, compared to just improvising without any input, is that you find things in this data that you wouldn't have come up with. So you get character out of it that you wouldn't have come up with yourself, because it's just not in your kind of expressive repertoire or something.
여기서 이제 아까 여기 화면으로 보셨겠지만 아주 다양하게 설정을 해서 정말 다양한 음악을 만들어 줄 수가 있고요. 그다음에 이 데이터를 통해서 혼자는 조금 만들기 어려운 그런 음악을 만들 수 있다는 것이 좋은 것 같고, 그래서 이제 더 캐릭터 있는 음악을 만들 수 있다고 합니다.
So I'll go back to the talk. So that? So we were asked by the people at CERN if we could, we were doing workshops with this approach, but that's always, what we were using there is a little bit like specialist thing. So they do a lot of stuff with kids and schools and young people, so they wanted to, asked if we could have something like this, similar to this, that we could use for teachers and things like this. So we came up with this thing called Ipsos, which is the Interactive Physics Sonification System.
저희는 그 다음 프로젝트로 어린이와 청소년들을 위한 그런 교육적인 것을 개발을 했는데요. 그래서 이 프로그램을 통해서 선생님들이 조금 사용을 할 수 있게끔 한번 개발을 했습니다.
And so we wanted something that would let younger people learn a bit about physics, but we also thought, well, why not learn a little bit about synthesis, specifically kind of classic ideas about sound synthesis at the same time.
저희가 아이디어를 내기를 물리학만 배우는 것보다는 이 사운드 신서시스를 같이 배우는 것이 좋을 것 같아서 이런 작업을 하게 되었습니다.
Okay, so I do a little demo of that now. Oops, sorry, that's the wrong thing. I'm just going to turn this down a little bit because this one is quite loud for some reason. So you get this website that looks like this, and you can see these are different collisions. And in this one, for example, you have two particles, and they have different values, and you can map these values to different synthesis parameters here.
이 웹사이트에 가시면 누구든 일단 사용이 가능하고요. 그래서 이제 여기서 충돌을 하나 설정을 하고 여기 다양한 선택지들을 선택을 하시면 음악을 만드실 수 있습니다.
And so if I play this now, sorry, it's still very loud. So I can play it as a sequence. So one particle being sonified after another, or I can play it as a chord. That's not bad.
이것 두 가지 충돌을 연속적으로 플레이를 시켜서 합성을 하는 소리를 만들었습니다.
These sliders here let you map the range over which the parameters will be sonified. So for instance, I can make the pitches lower.
음정을 낮추면 이런 소리가 납니다.
And then if I get a sound I like, I can add it to these presets here.
여기 이렇게 프리셋 이렇게 지정한 범위들을 저장을 한 프리셋을 틀면
And I can also select classic synthesis waveforms here. So square wave, triangle, sawtooth, sine. So let's try it like this. It's shorter. And I could then we could try something a bit different here. Let's make that a bit higher. With a different event. And then I can have a little performance with these presets.
이렇게 각각의 프리셋을 적용해 두면 이것들을 통해서 연주가 가능합니다.
Okay. And this is also comes with a bunch of information and materials for learning.
그래서 이 사이트에는 물리학에 대해서 조금 배울 수 있는 정보들을 함께 가지고 있습니다.
So you have sections here that tell you about the app, and then there's a section about aspects of particle physics, and there's a section about sound synthesis, and it explains simple envelope, and a section about sonification as well, with various resources.
여기 이 사이트에 이 앱에 대한 소개와 입자 물리학에 대한 배울 수 있는 정보들, 그 다음에 사운드 신서시스에 대한 정보, 그 다음에 소니피케이션에 대한 정보들을 담고 있습니다.
And I should say that these materials were prepared by Emma Margits and Milad Mardake, two composers. They did a really fantastic job of putting this together. Milad Mardake.
이 프로그램을 만드는데 밀라드 바디케이와 에마 마거슨이라는 버밍엄 대학교 학생들이 많이 도움을 줬다고 합니다.
Okay, so I'll turn that back up and go back to the talk. Okay, so why make an app like that? So from a pedagogical perspective, from a teaching perspective, it provides a way to engage students in things like synthesis and particle physics that's fun for them. And I think that's quite good. And there's this idea of playing, so they get to play with this. So when you engage people's creativity, we access different aspects of their intellect and of their personality. And from a musical side, it enriches the experience of audiences, and I mean this about the whole project, really. It somehow gives people this non-musical element in the real world on which to sort of structure and make their experience more meaningful. And I was really surprised by that when we started playing this for audiences, that people who might not have really liked what we were doing if we were just improvising found this really exciting. That somehow this related to this other thing that was in the world that they knew about, and that was of interest to them.
왜 이런 프로젝트를 하게 되었냐 하면 교육적인 관점에서는 그 학생들을 참여하게 하고 이런 소니피케이션이나 사운드 신서시스를 경험하게 하고 그것들을 통해 연주를 해볼 수 있다는 기회를 줍니다. 그래서 조금 더 창의성을 더 할 수 있습니다. 그리고 음악적 관점에서 봤을 때는 이런 음악적이지 않은 어떤 분야와 연결을 시켜서 더 의미 있는 작업이 되었습니다. 그래서 정말 좀 새로운 세계를 보는 듯한 그런 재미있는 경험이었습니다.
So this is just some pictures from workshops. These ones are from a school in North Wales, which was quite a nice place to go. It's a not very rich area, but and I think people don't often do workshops there, so they were really happy just to have people come. Although we did a performance actually for the parents, which I didn't know what they would think of it, and that, you had 40 11-year-olds with iPads improvising, which was a bit, from my perspective, kind of terrifying. But it was nice, I think, in the end. Emma was also there, and she was really good at helping with that.
이것은 워크숍을 하는 장면인데 노스 웨일스에 있는 초등학교에 가서 했고요. 이 지역에는 많은 사람들이 워크숍을 별로 오지 않아서 저희가 갔을 때 아주 기뻐했습니다. 그래서 이제 부모님들 앞에서 이 학생들이 직접 저 앱을 체험하면서 연주를 해보기도 했는데 그래서 정말 많은 아이들과 작업을 해야 했기 때문에 조금은 무서웠다고 합니다.
And this is in Athens, with some a little bit older students there.
여기는 아테네 학교이고요. 조금 더 큰 청소년들입니다.
Oh, and actually, sorry, I'll just stop that. But this is in Toronto at the Ontario Science Centre, and this is actually the first workshop that we did, and it was high school age kids. And I was really worried because they came in and they started making the sounds, and they were like, "Oh, it sounds like a doorbell, or it sounds like it's like, or it sounds like something rude or something." And I thought, "Oh no!" But then I realized actually it was great because they were laughing, and once they started laughing, I'm like, "Okay, they're laughing, they're paying attention, they're interested because it's funny for them." So they really had a good time, and I'll play it in a moment, and you can see that they're enjoying themselves.
여기는 토론토의 온타리오 사이언스 센터이고요. 여기에서 했을 때는 대상들이 고등학생이었습니다. 그래서 고등학생들이 뭐 도어벨 소리 같다, 뭐 이런 이상한 소리 같다 하면서 웃으면서 참여를 해서 선생님이 느끼기에 이 학생들이 집중을 하고 있구나 느꼈습니다. 그래서 아주 좋은 시간이었다고 합니다.
So a little quiet, but and we made them perform at the end.
여기 이제 요거 다음에 제일 마지막에는 연주를 해보기도 했습니다.
So it's a good lesson. It's okay if they laugh at you as long as they're listening. I think.
그들이 웃고 있는다는 것은 계속 들었다는 것이라고 생각합니다.
Okay, so this brings us now to this maybe last big phase of this project, which was this orchestra project. So I approached the Esprit Orchestra, which is an orchestra in Toronto which only plays contemporary music, to do a project based on this.
저희는 마지막으로 오케스트라 프로젝트에 대해서 이야기를 해볼 건데 에스프릿 오케스트라라는 오직 현대 음악만 연주하는 오케스트라와 작업을 했습니다.
And so it's a three movement work with orchestra, electronic sound, and video, and it's not live coded. It's all kind of done in advance, but it uses the same strategies that we used for sonification and visualization in the laptop ensemble stuff.
이 곡은 3악장으로 구성되어 있고 오케스트라와 전자음악과 비디오의 그런 퍼포먼스입니다. 그래서 앞에서 말했던 그런 소니피케이션 했던 방법으로 곡을 작업했습니다.
So the instrumental parts writing for the orchestra comes from the sonifications in three different ways. So there's a kind of straight sonification of the data. So like for instance, the entire first movement is basically one big sonification. So there's a sequences of pitch and rhythm which were just orchestrated directly, although slightly cleaned up and rationalized to fit metrical notation, so it was playable.
이 곡에서는 세 가지 방법의 소니피케이션이 사용됐습니다. 첫 번째로는 직접적인 소니피케이션인데 뭐 음정들의 연속의 나열이거나 다양한 뭐 리듬, 그다음에 이런 그 소니피케이션을 했을 때 조금 연주하기 불편한 리듬들을 조금 연주하기 좋게끔 고치는 그런 노테이션을 고치는 작업을 했습니다.
And so the second way was kind of imitative material that was inspired by the sonifications and similar to it. So you hear some of this in the second movement.
이 악장에서는 소니피케이션에서 영감을 받아서 모방적인 형태의 소니피케이션으로 활용했습니다.
And then the last thing is accompaniment, which draws on imitation or similar harmonic schemes to the sonifications that were being used.
그 사막장은 이제 그 반주로서 이 소니피케이션이 활용이 되었는데 이것을 조금 모방적인 것과 합쳐서 어떤 그 음계들을 보여주는 그런 악장이라고 합니다.
And then the visualizations were similar, as I said, to the ones for the live coding project, but they could be higher quality because I was doing them in non-real time. And they were created using Blender with some Python scripts that I wrote to drive Blender. I don't know if anybody here has used Blender, but it's ridiculous how much you can get into the guts of it with Python. And then the other advantage of Blender was that the University of Birmingham has a high-performance computing cluster which you can send jobs to, so I could basically get time on that to render the video, which was quite helpful.
비디오는 조금 더 퀄리티가 있는 작업을 위해서 실시간으로 만들지 않고 미리 만들었습니다. 이것을 블렌더라는 프로그램을 사용해서 만들었고, 그다음에 이제 버밍엄 대학교에서 아주 그 좋은 컴퓨터로 이 프로그램을 사용했습니다.
Okay, so I'll play a bit of this. I'm not going to play the whole piece because I think it's better to have a little time for questions at the end, but I'll play a little bit from each movement.
곡을 전체를 다 틀지는 않고 이제 조금 스킵해서 틀고 그 다음에는 질문을 또 받아보도록 하겠습니다.
Okay, so this is the first movement, which is called Clouds. And as I said, it's one big sonification with an accompaniment and a separate sonification of the same material in the electronics. And the video is inspired by cloud chambers, which I don't know if anybody's ever seen a cloud chamber, but they're actually a very early kind of actually particle detector. And they're very, very beautiful, actually, things. So I tried in my I'm a composer, first of all, not really, came to graphics and this sort of stuff later, but I tried in my way to get something of that sense.
1악장은 클라우즈라는 제목이고요. 그 커다란 소니피케이션이 반주로 깔리고 전자음악에도 소니피케이션을 적용을 시켰습니다. 그 다음에 화면 비디오에 대해서는 클라우드 체인버라는 입자 감지기가 있는데 그것을 비디오로 표현을 하고자 했습니다.
And I just say I might just jump around a little bit in this to show you slightly different things as we go.
그래서 이제 부분적으로 보여드리도록 하겠습니다.
Oops, sorry. I'll just jump to the end of this movement. Oops, sorry.
어, 1악장의 마지막 부분이었습니다.
So now we'll just do a little bit from the middle movement, which, as I said, has some more kind of imitative things. And this one is called Particles. Okay, I'll just jump ahead again. Oh wait, sorry. Let's catch the end of that. Okay, and then the last movement, which has visualizations which are closer to that original kind of spatial representation that you would get from the CERN visualizations. It's called Tapestries, and it's a reference to a quote by a physicist who talked about how modern physics it's not a work of art that one person does. It's like a tapestry that consists of the many, many threads that all the different people contributed. And when we went to CERN and performed there, I have to say I just found this like so inspiring because it's a worldwide effort there. They just had the first Iranian physicist had just arrived there. And it was really all of these people who came together to make these things possible. And I actually think that's a kind of wonderful model for what's possible and really, really inspiring.
이 3악장의 제목은 타피스트리라는 제목이고요. 어떤 물리학자가 했던 말이 있는데 모든 물리학은 여러 사람들의 노력으로 이런 결과가 난다는 그런 말에 영감을 받아서 이 곡을 작곡하게 됐고 이 프로젝트를 할 때 그 이란 물리학자도 참여를 했습니다. 그래서 정말 많은 사람들이 있었기에 이런 프로젝트를 할 수 있었습니다.
And I'll do the same thing again. I'll play the beginning of it and then jump ahead a little bit and catch the end because I want to make sure there's time for questions.
그래서 이제 앞부분과 끝부분을 연주해 보도록 하겠습니다.
Okay, so I think that's really about the end of it. A couple of thank yous there, but I'll just put this. This is the website for the web app if anybody wants to try it. So I'll just put it up there so you can. But yeah, that's.
이 웹사이트에 들어가시면 아까 보신 그 입소스라는 앱에 앱을 사용이 가능하십니다.
And so that's all I'm going to say. So I'll happy to have questions, but just before I take questions, I just wanted to say thank you to Gabin Kim, who's done a wonderful job translating, and I think deserves some applause.
Thank you.
Right. Okay. Yeah, so it works a little bit differently in each movement. In the first movement, there's just a couple of cues that happen, and it's very, very loose sync, so there's a kind of texture that just goes through, and as long as the conductor is roughly in time, it's fine. In the second movement, there's a number of sound sequences that get triggered at various points, and again, it's fairly loose because it's kind of irregular. And then in the last movement, a lot of it is like there's points where the conductor takes the beat, but they have to match the tempo that's in the sound, so they get the tempo from that. So it's quite rhythmic. So as long as he kind of takes that in his beat, it's fine. Does that answer your question? Kind of? Kind of. Or was it more about how I was making it, or when I was writing it, or you mean in the performance? The electronic things were all pre-recorded, but they were cut into little chunks so that there was some flexibility in with the orchestra. So mostly it follows the orchestra, and just you start things at particular points. Does that make sense? Yeah. Okay. Yeah. Yep. No, it's okay. So, when we're improvising, it's improvising, but we might have prepared some things to get us started. With the mixed piece, with the instruments and the electronics, you have to find some way of coordinating the parts, and there's different strategies for that. So there's actually in that piece, there's 3 different ways of doing it, in a sense. So. I don't know if that really answers your question, but you're right that it's a good insight that it's a problem you have to solve. It's good that you've recognized that. Yeah. Okay. Maybe you should. I don't know if do you want to try to translate all that, or is it too much?
Shortly. 그래서 조금 요약을 하자면 그 질문자분께서 이제 저 오케스트레이션 곡은 뭐 실시간으로 진행된 건지 미리 만들어진 건지 물으셨는데 오케스트라와 작업을 해야 했기 때문에 거의 미리 만들어져 있었다고 합니다.
Yes.
Firstly, he said, "Thank you for your interesting topic," and in a composer's perspective, he's wondering about, you said that there are many massive datas, and how do you select the important one?
Yeah, well, I guess there's two stages. I mean, one, that the data we get has already been identified as potentially important.
이미 데이터를 받는 당시에 그 중요한 데이터들이 선별되어서 받는다고 합니다.
But from a musical perspective, we might look for collisions that have a particular character. So I can just, so for instance, if I look here, you can see that this one looks in a particular way, but this is a good example. This one has a few particles which are in really close, and then one that is way out there. So you can see as I zoom out. So that's going to give me a particular kind of character. And actually, it's a good example maybe of the sort of thing that I might not have thought to do myself. I mean, if I just turn that back on again, if it'll still play. Sorry. And then if I you get to know a little bit like what effect it might have when you select a different one. Sorry, it was a lot.
그래서 어쨌든 그 중요한 것을 골라낸 정보들을 받아서 이렇게 다양한 음악을 만들 수 있는데, 아까 보였듯이 뭐 너무 이렇게 조밀하거나 너무 멀리 있는 것들도 사용을 해서 이렇게 음악을 만들 수가 있다고 합니다.
Anything else? Jorge, sorry. It's a mixture of informed guessing, because you never know exactly what it's going to sound like, right? But you know that if I look at something like this and I say, okay, this is what it looks like, and I map this parameter to pitch, I know it will have a certain sort of contour. So it's a mixture of informed guessing and just trying things. We worked with this data for years, and after a while you realize some things are more interesting than others. Use it from a musical perspective, yeah. An algorithm for deciding how to map it. Well, I mean, it depends what you mean. I mean, this is an algorithm in which I've mapped it, but I don't have another algorithm that changes the mapping, if that's what you meant. Yeah. Sorry, that's getting a little bit up in the clouds, but yeah. Do you want to try to translate that? Or? Oh, sorry. Oh, yes, sorry. Yeah. Of course. So by presets, you mean like when I'm selecting these? Yeah. So one of the things, it's a good question, because one of the things that we tried to do was bring out what we would call salient aspects of the data. So things that were important, that were meaningful about the data, right? And that's going back to what I said before, you can have a good visualization that hides important things, or you can have a good sonification or a bad sonification. So we tried to think about that. So one of the things about this list of collisions here is that the ordering of them is meaningless. It doesn't matter. There's nothing meaningful in terms of what they're seeing in the research about what order they come in. There just happen to be the collisions that happened in that order. So in a sense of how we were ordering them in terms of the different collisions, it's just a question of selection. There's no higher meaning to that. So in the orchestra piece, I just picked ones that I liked. So I tried different ones. Now, within an event, you've got the subatomic particles, and you can sonify them in some order, or you can sonify them in all at once, or you can do anything in between. One way is to just do them in the order that they're listed. Another way is you can see they sort of have two groupings, so they call those jets. So you can sonify jets. You can so there's different strategies you can do that might bring out interesting things about the data. But it also depends a little bit on the collision, because they all look really different. They all have quite different characters. I mean, I think that aspect of being able to change the data being input while the same algorithm is running was really successful. Like that was and quite a nice thing when you're improvising, because if you feel like it's getting stale, you just select a different event and you're kind of in a different world. So it's a long answer, but I hope that answers the question. Yeah. Okay.
Should we wrap up?
Yeah, I think maybe.
Thank you for your wonderful lecture today, and it was very interesting indeed. And thank you for coming to Korea for this festival.
Thank you so much for the opportunity to come and be here. It's been wonderful. Thank you.
Thank you very much. 그럼 지금까지 긴 시간 함께 해주셔서 감사합니다. 이상으로 스컬 윌슨 교수님의 암흑물질 새로운 물리학의 소리라는 강연을 마치도록 하겠습니다. 감사합니다.